We've now spent a couple of videos sorting out Landau theory, and we've mostly done it in the context of the Ising model. Remember that in that context, the order parameter had something to do with the magnetization, and the natural Legendre conjugate had something to do with the external magnetic field. This gave us a really nice laboratory for trying out everything that we wanted to sort of see about Landau theory. Now, I want to bring us back to our original model on which we learned about phase transitions, the van der Waals fluid. Can we use a similar description given that we know that this system has a second order phase transition at a single point, so it has a critical point? The answer is that we can, but we have to work pretty hard to get there. So in this video, I'm going to do just that. So first of all, what are we going to need right off the bat? Well, we're going to need an order parameter to be able to describe the system in this way. It's not super obvious what to do, but let me draw once again what happens when we look at our derivative of the Helmholtz free energy with respect to volume. So we get that curve that we were calling P naught. Now that'll be defined for a given temperature T. And let's choose T such that T is less than the critical temperature. Then we get something like this. Excellent. So this is the curve P naught. Okay. Now the order parameter, remember, should have a particular property. It should be non-zero at, and let me put this in quotations, 0h when T is less than Tc, but 0 at, once again, in quotations, 0h when T is greater than Tc. So it probably makes sense for me to get up here also one of these isotherms with T greater than Tc. Let me just mark in. So this is T less than Tc. And then we will do another one for when T is greater than Tc. Okay. So what is spontaneously non-zero? If we pick, for instance, a given volume, the answer is that the simplest thing that we can pick to be our order parameter is the difference between a given volume and that volume's corresponding volume in the other phase. And let me show you what I mean. Suppose that we're interested in this volume. We know that this is in the gas phase. Remember that the gas phase is over here further to the right. And yes, let's work in reduced units. So I'll non-dimensionalize everything. So I'm actually going to turn this axis into nu, the non-dimensionalized volume, V over 3NB. And we can turn our pressure axis into, let's say, psi. Where psi will be similarly non-dimensionalized in some way. Now, I'm choosing this non-dimensionalization such that the critical point happens at the point nu equals 1 and psi equals 1 at temperature T equals Tc. We could also work in units of reduced temperature, and we'll get there in a second. But in any case, we're interested in this volume nu. So what I'm going to do is go up to where I hit that point on my psi curve. Now this is, I guess, psi naught. And to determine the value of the order parameter, I'll just follow this to the left until I get here. So I'll find the other volume, which I'll call nu sub L, that is at the same pressure. Then I'll look at this difference. And this difference will be my order parameter, phi. Notice that if I try to do the same procedure on this upper line, the line for T greater than Tc, well, there's nowhere to go left. there's only one phase, which is neither liquid nor gas. So in that case, the order parameter is 0, as we would want. And when when T is lower than Tc, we should always get phi being non-zero for certain values of the pressure. And that's exactly what we want to see. Excellent. So, well, this is great. We can just do exactly what we did for the Ising model. Our naive goal at this stage, what am I doing? Would then just be to write down the Helmholtz free energy. So we could write little f, which is typically capital F over nkbTc, is equal to some polynomial in the order parameter. And then we could do just exactly what we've done in the past. We could Taylor expand, or I suppose it becomes a polynomial once we've Taylor expanded. And then we can see everything that we want to see using Landau theory in the way that we did in the last video. But we immediately encounter a problem, which is that phi is not even well defined. It has it never takes any values other than 0 when t is greater than tc, based on the definition that we've given here. So in fact, if we were to draw out what phi, where phi can take which values I should say phi can take, let's let this be the t-axis, and this can be the point tc, and this can be the phi axis, and I just want to color in where we can actually get phi being, or where we'll get phi's at all. We have something symmetric like this. Now we'll define negative phi's if we started in the liquid phase, so with a volume down here. Then the rule is going to be that we go across this way, just as we did before, but now phi is negative. So we'll always get pairs, negative phi's and positive phi's. In any case, we get something like this. And really all we can do with this is make some educated guesses about how to fill in other values of phi and then get f. So we could say, for instance, that we're going to fill in all of the phi's in these other regions. So let's say that we're going to fill in all the phi's in here and over here, and for t greater than tc, so everything up here too. But we're going to do that in such a way that we never, when we do the Legendre transform, actually end up hitting a value in this pink region. So we'll never actually assume that value of phi. And so it doesn't matter that we've filled in these extra values. This would be the process of analytic continuation on the function f. And it would be one way to approach what we're doing here. But I have to tell you, this way is not pretty. Because this was a cubic function to begin with, this psi naught curve, doing everything that I've shown here becomes very gross very quickly. So in order to try to figure out how this compares to the Landau theory for the Ising model that we've already seen, I'm actually going to take a totally different approach. I'm not going to worry about the free energy anymore. All I'm going to do is try to find the critical exponents based on this curve. Okay, I'm going to clean up the board a little bit and then I'll start doing that. Okay, we're back. So over here in this corner, I've shown what all of these critical exponents have as their definitions. Remember that the beta exponent has something to do with the value that phi takes at h equals 0. I still have to get to what that means. The delta exponent is given to us by how phi star changes with h at the critical temperature. And lastly, the gamma exponent has to do with how this derivative of phi star changes at h equals 0 with temperature. Okay. Notice I haven't put the alpha exponent up here. It's just not worth our time to do that one in addition to all three of these. But it could be done in the same way that we're doing all of them. All right, wonderful. So now I do need to talk about what I mean by h equals 0 here. Remember that for the Ising model, the point h equals 0 was the value of the magnetic field for which we saw a switch from one phase to the other. For the Ising model, this meant from the spins being mostly up to the spins being mostly down. That value for the van der Waals fluid will not be zero pressure. Zero pressure has nothing to do with where this switchover point occurs. In fact, what's really unfortunate here is that this switchover pressure depends on the temperature. We saw that the switchover pressure is given by the Maxwell equal area construction that we've already seen in previous lectures. So, okay, we're just going to have to replace h equals 0 with psi equals psi switch, which will be something that depends in this case on temperature. All right, so without further ado, let's just launch into it. Now, let's remember what our definition for this object was. When we did this derivative, we found that psi naught is equal to 8 tau over 3 nu minus 1 minus 3 over nu squared. Now I have decided to switch to reduced temperature tau, which is just going to be T over Tc. Good. Working in these non-dimensionalized units will make our lives quite a lot easier, so there's reason to do it. Okay, now immediately it would be possible, it at least would be conceivable to write nu as a function of phi and then just proceed from there. But nu turns out to be a very complicated function of phi, so I'm not going to do that. Instead, I'm going to note that the 2 points that we care about on our curve, the two with the same pressure, but with one with a volume in the liquid phase and one with a volume in the gas phase, can be sort of equated in this equation. So I can do the following. So 8 tau, because these are on the same isotherm, over 3 nu liquid minus 1 minus 3 nu liquid squared is equal to 8 tau over 3 nu gas minus 1 minus 3 over nu gas squared. So now I have an equation that depends only on these two different volumes, one in the liquid phase and one in the gas phase. All right, wonderful. We'll see that by rearranging this equation, I can get something that does depend on our order parameter phi. Okay, so to do that, I probably want to clear denominators or maybe move some things around. Let's start by just moving a couple of things around. We know that nu liquid is smaller than nu gas, which means this denominator is bigger. So if I move this 8 tau over 3 nu g minus 1 over, I'll get something positive. So let me do that. 8 tau times 1 over 3 nu L minus 1 minus 1 over 3 nu G minus 1 is equal to, now I want to move the 3 over nu squared terms all to one side. So there we'll get 3 times 1 over nu L squared minus 1 over nu G squared. Great. Okay, and we can go somewhere with this. If we find a common denominator for this term on the left, you'll notice that we'll get a 3 nu g minus 1 minus 3 nu L plus 1. So the minus 1 and plus 1 cancel. We can pull out a 3, so that will leave us with 24 tau. And then we'll get nu g minus nu L over 3 nu L minus 1, 3 nu G minus 1. And that will be equal to, well, on this side, we'll have that 3 still. Then, when we find a common denominator here, we'll pick up nu g squared minus nu l squared. But that's a difference of squares, so we can factor it. And we'll get nu g plus nu l times nu g minus nu l all over nu l squared nu g squared. All right, we get some nice cancellations now. We can divide by 3 to get rid of that. Notice we have a nu g minus nu l on both sides. We know that's not equal to 0 because I guess I have sort of jumped to conclusions here, but I'm assuming that tau is less than 1 or t is less than tc. So the volume in the gas phase is definitely greater than the volume in the liquid phase. Good. And now we're basically home free. We can rearrange this equation however we want. I'm going to rearrange it to solve for tau. So I'll move everything else to the other side. So we'll finally get tau is equal to 3 nu L minus 1 times 3 nu G minus 1 times nu G plus nu L all over 8 times nu L squared nu G squared. Excellent. So now we can rewrite this equation in terms not of nu L and nu G, but in terms of our order parameter and something else. And actually, it's not terribly hard to see what we want to do. If we choose one object that looks like the sum of nu G and nu L, and then one that looks like the difference, which will be our order parameter, then we can rewrite this equation pretty simply, just with that linear transformation. So let's define nu bar to be the average of nu G and nu L. And once again, we'll have phi, which is nu G minus nu L. And I'm going to skip the algebra here and just write the result. Which is that tau is equal to, oops, no 2. Nu bar times 4 times 3 nu bar minus 1 minus 9 phi squared over 4 nu bar squared minus phi squared squared. Okay, excellent. So what has this allowed us to do? Well, it's allowed us to write tau as a function of nu bar and phi. Now the key is that as we approach along the curve, such that we're always at psi switch, nu bar will have a Taylor expansion in phi with a 0th order term. But phi, obviously, will not have a Taylor expansion with a 0th order term, precisely because the critical point happens when phi equals 0. So let's be really clear about that. The critical point occurs when phi is equal to 0. Okay, so if we do that approach, we can replace, so we can think of tau as a function of phi again. Nu bar is a function of phi in the sense that we're approaching along a particular curve. which is one-dimensional. So it should be able to be parameterized just by phi. And the way that we would do this is to actually say that nu bar is a function of phi and the pressure, but we know that that pressure is going to be p switch for every value of tau. So, okay, when all is said and done, we can replace nu bar by its value, by the 0th order term in its Taylor series, which will be its value at the critical point. But at the critical point, nu g is equal to nu L, which is equal to 1. Uh, so nu bar will also equal 1. So what we'll find if we do this is that tau is approximately equal to, in the region around the critical point, if we're evaluating at psi is equal to psi switch, tau is approximately 1 minus 1/16 times 1 plus 6 nu bar prime of phi at phi equals 0, and then times phi squared. Okay, the key is that tau does not have a first order term in phi. So it only has a squared term in phi. Now, if we look at our definition of beta, and we replace Tc minus T with 1 minus tau, which would be what happens if we just pull Tc out, then we see that we want to see how phi depends on tau, or sorry, on 1 minus tau. And here we see the answer. Phi goes as 1 minus tau to the 1/2, which we would get if we just rearranged this. Given that this term is all a constant, the coefficient of phi. Excellent. So we have our first answer. Beta is equal to 1/2 in this case. And just for comparison, its value for the Ising model is also 1/2. Okay, time to clean up the board and get to the next critical exponent. Okay, next, let's find the delta critical exponent. For that, we're going to need to rewrite our equation here, which is that psi naught is equal to 8 times tau over 3 nu minus 1, oops, minus 3 over nu squared. Excellent. But notice that we're supposed to look at t is equal to tc. If we do that, then we're golden. We find tau is equal to 1, and we're all good. We would just look at this equation. But once again, we find a problem. And that problem is that business about phi not actually ever taking values other than 0 when t is greater than or equal to tc. So this wasn't necessarily true in the Ising model, but it is true here. We just don't have a definition of phi that permits values of phi other than 0 at temperatures greater than or equal to the critical temperature. So the only way to really look at this exponent is to set t to be just less than tc, and then do everything that we would normally do, and then just sort of ignore the fact that, or ignore terms that are small. So let me be really clear about what I mean here. I'm just going to set tau equal to 1 minus epsilon, where epsilon is going to be a very small number. And what I'll do is ignore terms of order epsilon when I finally go to look at delta. Excellent. So this equation is going to give us everything that we want. And the way that we can see that is if I split off the epsilon term here. Okay, so I'm going to do 8 over 3 nu minus 1 minus 3 nu squared minus the quantity 8 over 3 nu minus 1 epsilon. Wonderful. Now, if I look at this as a function of nu, and then I do a Taylor expansion about nu equals 1, which is the exact value for the critical point for nu, then there's something that I immediately know. And it's based on what this curve looks like when we have tau is equal to 1, which is what's happening in these first two terms. Remember that when I have tau is equal to 1, that corresponds to there being an inflection point here, a point where the second derivative is exactly 0. But if the second derivative is 0, then that means the Taylor expansion at exactly tau is equal to 1 will have nothing in the, we'll have a 0th order term, but then no first order term and no second order term. So this is all going to be equal to some psi value, which in fact we know will be 1, the value of psi at exactly the critical point. Then plus, well, maybe we can just say psi naught triple cube, or triple derivative of nu at nu equals 1 times nu minus 1 cubed. And then we get some stuff of order epsilon. But as we said, we're going to ignore that anyway. So this was actually not so bad at all. We have a relationship between the value psi naught minus 1 at the critical point and nu minus 1. Okay, so let me write that down. So nu minus 1 goes like psi minus 1 to the 1/3 near the critical point. But there's an issue here. This gives us the relationship between nu and psi and not between phi and psi, which is what we actually need. Okay, how are we going to deal with that? Well, the answer is that we need to also think about the Taylor expansion of nu in terms of phi. And there, we don't need to be too careful. We know that nu of phi will have some Taylor expansion. And then in particular, assuming that we are interested in a point just below the critical temperature, this Taylor expansion will look like the following. At phi is equal to exactly 0, nu will be exactly 1. So we'll have a 1. If we're expanding about phi is equal to 0. And then we'll get plus nu prime of phi times phi plus dot dot dot. But it's not too hard to see just pictorially that there's no reason the first order term should vanish. So here we'll have phi goes like nu minus 1 in this region. And stringing these together, that implies that phi goes like psi minus 1 to the 1/3. So you'll notice that in a lot of this math, there's a lot of just seeing where terms in the Taylor series must vanish and where they don't need to vanish. And that's something that you'll just have to get used to as you work with this kind of critical behavior math. All right, wonderful. So we see here that delta is 3. And I want to remind you that for the Ising model, we also found delta was 3. Excellent. Okay, one last critical exponent to compute, which is the gamma critical exponent. Now, this one is going to be a little bit harder, so let me clean up the board and then we'll figure it out. Okay, it's time to compute our last critical exponent, gamma. Now, for this one, we're going to need to use some clever tricks. The first clever trick is that in this case, oh, and I actually have this wrong. We don't necessarily need t is less than tc. We just need that t is not exactly equal to tc. So we're actually going to approach tc from above in this case, which is going to make our lives a lot easier. Okay, So how are we going to make all of this work? The answer is that we're going to use a partial derivative identity that we've used quite a lot in thermodynamics. And we're going to look at d psi d phi rather than d phi d psi. And then whatever exponent we find, we know we'll just need to negate, and that will give us the correct answer. Now, dealing with this h is equal to 0 business is going to be a little bit tricky, but we know that we get the switchover point where phi is equal to 0. So we'll be all right if we just set phi equal to 0 in the end. Excellent. So we basically have a strategy here, but I'm actually going to make one more simplification as well. So let me say, can examine this. We know that phi near the critical point is approximately equal to nu minus 1 times possibly some constant. But the constant won't matter for calculating these exponents. So actually, we can just examine d psi d nu. And we'll be good. Okay, so let's do it. What we're going to do once again is write our psi naught, 8 tau over 3 nu minus 1 minus 3 over nu squared. But in this case, notice that psi naught really just is psi. There's only one real solution here, so we're all right. Okay, so now we want to expand. Basically, we want to expand this in nu, or we could just say we're going to take the derivative in nu and then evaluate it nu is equal to 1. Okay, let's do it. So d psi d nu. I can replace psi naught with psi comfortably because we only have one solution in this regime. Is equal to, let's see, 8 tau times 3 nu minus 1 squared. So that is just treating this thing in the denominator like a variable, taking the derivative with respect to that. We'll also pick up a negative sign from that. Good. And then from the chain rule, we get 3, so that 8 turns into a 24. All right. Next, we need to do the derivative of this second term. So we can think of this as minus 3 nu to the minus 2. So this can become plus 3 over nu cubed. Great. Okay, so the next thing is we need to set nu equal to 1. And see what we get. So in the denominator here, we'll get 2 squared, which is 4. So we get minus 6 tau plus 3 over 1, just 3. Good. And what we see is that modulo this constant term, which is just going to have something to do with the 0th order behavior, as we approach the critical temperature, we're going to get that this has just linear behavior in tau. Okay, linear behavior in tau means that partial phi, partial psi should have inverse linear behavior in tau near the critical point. Okay, so that means that dh phi star should go like 1 minus tau to the minus 1. Or in fact, because we're approaching from the other side, it's actually tau minus 1. All right, awesome. Which means that we get gamma is minus 1. And once again, We see that the easing model has the exact same critical behavior. Okay, so this was a very, very long-winded, algebraically technical video, but really we came to a really interesting and conceptually simple conclusion, which is that very different seeming systems sometimes have critical behavior that is very similar. So, because we can always define, in terms of the order parameter, these various quantities, we can make comparisons across systems that don't really have physical parameters in common. And in this case, it turns out that the van der Waals fluid and the Ising model in high enough dimensions have exactly the same critical behavior. In terms of these universal exponents. This is a property or phenomenon called universality, and it makes up a lot of what people are interested in modern statistical physics. It's very interesting that with, a medium amount of work, we were able to see it on display in these two very simple systems. Now, it's interesting to note that neither of these models, neither of these toy models, really comports with the experimental data for similar systems. So, if rather than looking at the Ising model, we look at ferromagnetic systems, and rather than looking at the van der Waals fluid, we look at real liquid gas transitions, we don't find exactly these exponents, which speaks to some more complicated behavior that goes on in the real world that we're not capturing in these toy models. Nevertheless, models that do share universality often share other features that make them easier to study in certain ways. I won't go too much more deeply into this, but this is something you might encounter in a graduate level statistical physics course. So I encourage you to look into that material if you're interested. Thank you so much for watching this video, and I will see you in the next one. This is our last video in classical thermodynamics, and in the next one, we're going to start a brand new topic in which we'll talk about the dynamics of, of thermodynamic systems for the first time. Thank you so much for watching.